In this video, we're going to be looking at 3 examples where we use the tool of integration to create new power series representations. In this example, we have the function f of x equals log of 1 plus x, and I want to try to use integration to find a power series representation for that function. So the first thing that we want to note is that the integral of 1 over 1 plus x dx would be equal to log of 1 plus x plus c. Okay, so if I had a power series representation for 1 over 1 plus x, I could use that to find a power series representation for log of 1 plus x. What we do know is the power series representation for 1 over 1 minus x. We know that that's the sum from n equals 0 to infinity of x to the n, where the absolute value of x is less than 1. Okay, so notice that I can find the power series representation for 1 over 1 plus x as an initial step here. I know that 1 over 1 plus x could be rewritten as 1 over 1 minus negative x. So this would be the sum from n equals 0 to infinity of negative x to the n, where the absolute value of negative x is less than 1, which is the same thing as saying the absolute value of x is less than 1. So this series would be the sum from n equals 0 to infinity of negative 1 to the n x to the n. Okay, so to integrate 1 over 1 plus x, I could integrate the sum from n equals 0 to infinity of negative 1 to the n x to the n dx. Okay, and since I know that this integral here is log of 1 plus x, okay, that's going to help me get my series representation. So notice that the integral of this sum is going to be the sum of the antiderivatives of each term. Negative 1 to the n remains unchanged. That's still negative 1 to the n. It's just a constant. And then I'm going to have x to the n plus 1 over n plus 1 and plus c. Okay. Let's see here. A couple of things that we want to note. One is I need to solve for plus c, because I actually have a known function over here on the left-hand side. So let's do that first. So we're going to solve for c. So if that equation has to always be true, then it would have to be true for all values of x. So I could just plug in a nice value for x to help me solve for c. So if we plug in x equals 0, notice that that left-hand side will be log of 1. If I plug in x equals 0, this sum will just be a sum of zeros, and we know that log of 1 is 0. So we see that c would have to be equal to 0. Okay, so what about why I have absolute value bars here and not on the original function? Well, if I need my absolute value of x to be less than 1, that means x is between negative 1 and 1. Okay, and 1 plus x is greater than 0 when x is greater than negative 1. Okay, so because we will have x greater than negative 1, actually also less than 1, log of 1 plus x will always be, or 1 plus x itself will always be positive. So we can say log 1 plus x without the absolute value bars here is equal to this sum from n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. Okay, that still has a radius of 1. Okay, now it turns out when we integrate, we know that our interval of convergence could change. Okay, when you integrate, your interval could potentially increase in size, meaning perhaps in the original function you didn't include one of the endpoints, and when you integrate you might end up including one of the endpoints. So I'm not going to go through the work here, but it turns out that here we have x can be between negative 1 and 1, including 1 and not including negative 1. Okay, so we have this power series representation for our log function. Oftentimes this is just indexed slightly differently. So I just want to note that you'll probably see this expressed in the book as a sum from n equals 1 to infinity with negative 1 to the n minus 1, x to the n over n. So notice here when n is 0, I would have a positive power here. Negative 1 to the 0 would be 1. When n is 0, this would be x to the 1 divided by 1 here. Notice that when n is 1, I'm going to get negative 1 to the 0, x to the 1 over 1. So this just reindexes it and tends to be the form in which this is often stated. Okay. And this is for x between negative 1 and 1. So let's look at a couple of other examples of series that we can find using our integration tool. So recall that in one of our previous examples, example 1, we found the power series representation for 1 over 1 plus x squared. And we found that that was 1 over 1 plus x squared equals the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n, where the absolute value of x was less than 1. Okay. And now we're being asked to use integration to find the power series representation for arctangent. Well, notice that the integral of 1 over 1 plus x squared is our arctangent function. Okay, so to get a power series representation for that, I can integrate the power series for 1 over 1 plus x squared. So that means I want to integrate this sum of negative 1 to the n, x to the 2n dx. Okay, so I'm going to have the sum from n equals 0 to infinity, negative 1 to the n, just a constant, and I'll have x to the 2n plus 1 over 2n plus 1, and then plus my constant of integration. So because I have, again, this known function on the left-hand side here, I can solve for c. So we can plug in a nice easy value for x, like x equals 0. So notice that I could have arctan of 0 equals, well, this will just be a sum of zeros plus c. Arctan of 0 is 0, so I'll find that c equals 0. Okay, so we can say that our arctangent function is equal to this sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1, all over 2n plus 1. I know when I integrate, the radius of convergence stays the same, so it's still going to be r equals 1, but the convergence at the endpoints could change. With some additional work, we could show that I would actually include both of the endpoints in this case. So I'm not showing the endpoint work, but I'm just stating what the interval would end up being here. Okay, so now we have yet another power series representation for a new function, and I could do some additional things with that function. I could find, for example, a power series representation for arctangent of x squared by manipulating this series. Okay, so this tool here has allowed us to create a lot of new series that we can then use in various problems. Okay, so we're going to look at one final example that's going to have us use the integration tool in a slightly different way. So here I'm given that log of 1 plus x is equal to this sum from n equals 1 to infinity, negative 1 to the n minus 1, x to the n over n, where x is between negative 1 and 1, not including negative 1, but including 1. And first I'm asked to find a power series representation for x squared of log 1 plus x. So recall that we used integration to find this series representation. Now I can manipulate that series. So I can say x squared log of 1 plus x is equal to x squared times my series representation for log of 1 plus x, which is this sum from n equals 1 to infinity, negative 1 to the n minus 1, x to the n over n. Okay, and then I can move the x squared inside the sum. So I have n equals 1 to infinity, negative 1 to the n minus 1, x to the n over n times x squared. Okay, which means I have this sum, negative 1 to the n minus 1, x to the 2 plus n, or n plus 2, all over n. Okay, where this is again for x between negative 1 and 1. Okay, so now we have a power series representation for x squared log of 1 plus x. So we can use that to integrate x squared log of 1 plus x dx. So we're trying to integrate this as a power series. So this means I need to integrate this sum from n equals 1 to infinity of negative 1 to the n minus 1 x to the n plus 2 all over n dx. Okay, and so power series are a really useful tool for helping us take integrals of things that might be otherwise not possible to do or even just a lot more complicated to do. It's really nice to take integrals of power series because we're just integrating essentially really long polynomials, and polynomials have really nice antiderivative rules. So here I'm going to have my sum from n equals 1 to infinity. The negative 1 to the n minus 1 part stays the same, that's just a constant. This will be x to the n plus 2 plus 1, so n plus 3 all over n stays the same, that's just a constant, and then times my n plus 3, and then plus my constant of integration. So here we don't solve for c like we did before, because I don't have some known function that is my antiderivative. This whole thing is my antiderivative of x squared log of 1 plus x. Okay. We know that the radius of convergence would still be 1 because the radius of convergence doesn't change when we differentiate or integrate, but with some additional work we could show that the endpoints actually end up being included here. So this would actually be the antiderivative here for all x between this series here would be equal to the antiderivative of this function for all x between -1 and 1. Okay, so let me know if you have any questions on this material.